The usual physics terminology for motion that repeats itself over and over is periodic motion, and the time required for one repetition is called the period, often expressed as the letter t. The symbol p is not used because of the possible confusion with momentum. One complete repetition of the motion is called a cycle. The frequency is defined as the number of cycles per unit time. Frequency is usually denoted by a Latin letter F or by a Greek letter V. Note that period and frequency are reciprocals of each other. F is equal to 1 over t. For example, if a newborn baby's heartbeat at a frequency of 120 times a minute, its period, the interval between beats, is half a second. If you calibrate your intuition so that you expect large frequencies to be paired with short period and vice versa, you may avoid some embarrassing mistake on physics exam. Angular frequency. Often periodic motion is best expressed in terms of angular frequency, represented by the Greek letter omega. Angular frequency refers to the angular displacement per unit time, example in rotation, or the rate of change of the phase of sinusoidal waveform, example in oscillation and waves, or as the rate of change of the argument of the sin function. Y is the period equals to sin open close parenthesis period is equal to sin open close parenthesis angular frequency period is equal to sin open close parenthesis 2 radians frequency period. Angular frequency is equal to 2 radian frequency. Angular frequency is often represented in unit of radians per second. Recall, there are 2 radians in a circle.
Hooke's law. The simplest oscillations occur when the restoring force is directly proportional to displacement. The name that was given to this relationship between force and displacement is Hooke's law. F equals kx. Here, F is the restoring force, x is the displacement from equilibrium or deformation, and k is a constant related to the difficulty in deforming the system. Remember that the minus sign indicates the restoring force is in the direction opposite to the displacement. The force constant K is related to the rigidity or stiffness of a system. The larger the force constant, the greater the restoring force, and the stiffer the system. The units of K are newtons per meter, close parenthesis, n over m. For example, K is directly related to Young's modulus when we stretch a string. A typical physics laboratory exercise is to measure restoring forces created by springs, determine if they follow Hooke's law, and calculate their force constants if they do.
Mass on a spring. A common example of an object oscillating back and forth according to a restoring force directly proportional to the displacement from equilibrium. Example following Hooke's law is the case of a mass on the end of an ideal spring where ideal means that no messy real-world variables interfere with the imagined outcome.
We can understand the dependence of these equations on m and k intuitively. If one were to increase the mass on an oscillating spring system with a given k, the increased mass would provide more.
Good morning everyone. I will be the one who will discuss the topic about simple harmonic motion and uniform circular motion. Simple harmonic motion is a type of periodic motion where the restoring force is directly proportional to the displacement. It is often modeled with the example of mass on a spring where the restoring force obeys Hooke's law and is directly proportional to the displacement of an object from its equilibrium position. Any system that obeys simple harmonic motion is known as a simple harmonic oscillator. The equation of motion that describes simple harmonic motion can be obtained by combining Newton's second law and Hooke's law into a second-order linear ordinary differential equation. F net is equal to md squared x over dt squared is equal to negative kx. Uniform circular motion. Uniform circular motion describes that the movement of an object traveling a circular path with constant speed. The one-dimensional projection of this motion can be described as simple harmonic motion. In uniform circular motion, the velocity vector v is always tangent to the circular path and constant in magnitude. The acceleration is constant in magnitude and points to the center of the circular path perpendicular to the velocity vector at every instant. If an object moves with an angular velocity around a circle of radius centered at the origin of the x to y plane, then its motion along each coordinate is simple harmonic motion with amplitude and angular frequency.